Good day, and welcome to TD Physics. Thank you for joining me as we explore projectile motion, non-horizontal launches. Lewis King was from Cedardale, Ontario, about 50 kilometers west of Ottawa. He was a rubber worker, worked in the auto industry, and he enlisted November 15th, 1915. 5'10" or thereabouts, blue eyes, black hair. Less than 3 years later, he would sign this. I, Lewis King, formerly the gunner in the 45th Battery Battalion, bearing the regimental number 438509, hereby certify that I have received from the Invalided Soldiers Commission an artificial leg of the government pattern which is satisfactory to me in every respect. The limb is according to specifications and a satisfactory fit. An ominous diagram ensues. It's the world of artillery that we explore today in projectiles that are launched not horizontally.
I just made sure it was level, and the angle looks like it's... How do I read the angle?
So you read it in mils.
Right here, so 50 mils.
Yeah, we're at 50 mils, and then we're going to add whatever we read in black here. It says 0, so it's going to be 50 mils even. So we'll go translate that. I believe that's about 3 degrees, but we'll have to translate that back at the ranch. So this is what we're measuring here. This is a very, very big field gun here in the Woodbridge area. And we're trying to figure out the angle it would shoot above horizontal. We're here at the Woodbridge Memorial at the Cenotaph. This is one of the field guns that is stored there. And this is a World War II artillery piece that would help calculate what angle. The units are in milliradians. This dial here would allow you to dial in your angle within 0.2 milliradians. So by moving this knob a little bit, you can see that the bubble has moved ever so slightly the other direction. So if artillery equipment was capable of being plus or minus that fine a degree, well, clearly we must be able to do some physics to predict where projectiles will land. Now, we are going to assume that in grade 11 physics that there's no such thing as our atmosphere. Obviously, in real life, this would be much more complex. But vertically, what we'll find is that our objects that we have fired, our shells in this case, are going to travel at a constant velocity horizontally, but they will accelerate vertically downwards due to gravity. Okay, so we're going to be launching at an angle. And so that means that if we're going to fire at an angle, above or below horizontal, we're going to have to declare directions to be positive. That's going to be super important, especially now. And we're going to be working on breaking this into its horizontal and vertical components. So just like a right angled triangle, if you know the angle and the hypotenuse, you can find the other sides. Lewis King was seriously injured on the battle for Hill 70, one of the more forgotten but very important battles that Canada was exclusively responsible for capturing near the city of Lens. So 4 months after Vimy Ridge, Canada was called on to attack Lens, a bombed out city just below them. But there was the high ground that was held by the opposition, by the Germans. Slightly ignoring those orders, General Curie and his men lay down a creeping barrage. A creeping barrage is when you always launch your projectiles just a little bit further every time to give covering fire for your infantry. And they captured it at great cost. And so once they had captured it, they could see all of the valley below them. So if you were on top of Hill 70, called such because it was 70 feet above sea level, and then stretching below it was a lower valley, how far could a gun like this that you can see in this picture fire? Well, it depends on how fast the gun can shoot, the angle that it shoots at, and the height above horizontal. So if this is going to be our rough diagram right here, So our cannon is going to be on top. We're not even going to draw it, but our cannons at the Woodbridge Memorial here in Woodbridge are at, so they're at 3 degrees. That's not very much. I'm going to draw it slightly bigger than that just to emphasize that there actually is a component here. And I'm going to draw in some horizontal and vertical components. You've worked with components in the past in the context of displacement. Now we do it in the context of velocity. If you look closely at the guns at the memorial, they'll say Krupp. That's a German gun maker. Just for the record, guns are the big honking things that fire shells. Rifles are what fire bullets. And so this was a very long version, so it could fire at approximately 850 meters per second. That is extremely fast. And our angle in here is 3 degrees. First of all, we're going to look at how far could this fire, and then we're going to look at, well, what would happen if we just added just 1 degree, a tiny little change. It'll be significant. So this is our diagram. We want to figure out where is this going to crash over here. So this will make an arc through the air, and eventually it'll come down. This is not really a good parabola, but we don't have space for it. So if this was 40 meters above the ground below it, holding the high ground was essential for winning a war. You could see farther, you could shoot further, and you were safer from enemy guns. So that's 40 meters there. Our horizontal range is unknown. And so what do we know from here? Well, the first thing we can do is we can break this into components. This side right here is adjacent to the 3 degrees. So we can use cos of 3 degrees, put that in brackets, I suppose, times 850, that's our hypotenuse, is going to be our adjacent. So I've just taken the hypotenuse down here and brought it up top. If we look at that result, that side should be equal to essentially 850. We'll say 849 meters per second. And our vertical component right here, sine of 3 degrees times 850. It's a little bit more convincing at 44.5 meters per second. So that's how fast it's going up. And it's going 849 meters per second to the right. We need to declare some directions to be positive. And so this being up, let's not forget to identify that as a negative velocity. Okay, so we're going to solve these similar to what we've done before. Set up a vertical and horizontal table here for our different data. So vertical goes here, horizontal goes here. In the vertical, we've got 5 kinematics data points. In the horizontal, we only have 3 because our velocity doesn't change. So there's no V1, V2, or acceleration. Okay, so some things we do know: acceleration due to gravity over in France, and similarly here in Canada is 9.8 meters per second, or 9.8 meters per second squared. Our vertical velocity is going to drop 40 meters, so that's going to be a positive. Our V1 is no longer 0. Okay, so that's going to be 44.5 meters per second. Remember, this is up, and we said down was positive, so that's going to get a negative. It's also important enough that it's going to get a highlight. Our horizontal velocity is essentially the same as our hypotenuse. This will change more obviously as the angle gets steeper. Our times are the same. This is our range, and V2 is unknown. Now for this problem, I'm not going to ask for impact velocity. I just want to figure out what its range would be. But impact velocity is easy enough to calculate. You just have to calculate V2 and then add V horizontal to it. We've done in previous problems. But for now, we want to figure out how far does this go. Now, if we use the equation that we have used in the past, we can, but notice that this is going to result in a quadratic equation. You don't know time, you do have a d, you do have v1, you do have acceleration, so you are welcome to do this if you would like, but quadratics are not my friend. They're a lot of work, they're time consuming, And often you have to find your impact velocity anyhow. So if that's the case, if we can find a way around using a quadratic, I'd like to. So this is going to be where I'm going to start. A little bit different than before. If I ignore time, I can find V2. And if I can find V2, I can use a different equation to then go and find my displacement. So V2, that's our vertical velocity when it hits the ground just before it touches. The negative is going to come inside a bracket here, get squared and go away. And acceleration is 9.8, and your vertical change of position is 40 meters down, so that's a positive. And if we crunch these numbers, we should come to V2 is equal to approximately 52.6 meters per second. This will give us a plus or minus value. Remember, it's the square root that we have to do. And so we're going to take the plus on this one because it's going downwards. Now with that number, we'll do a quick check-in. So with this going up at 44.5 meters per second and no atmosphere, when it comes back down to the same level, it should be going at the same velocity. And then it's got to drop another 40 meters. So it should be going 44 plus some, and 52.6 is a reasonable number. So I think that we've got this. It's certainly not 2,764, which is what all of this adds up to, if we forgot to square it. So I'm going to use a different equation now. V is equal to V1 plus V2 divided by 2 times time. You know this from your kinematics equations when we don't know acceleration. We plug in our values here. If we're going to find our time, not using a quadratic, V1 in this case is negative 44.5. We're adding 52.6, dividing by 2, and multiplying all of that by time. If we do that, time is going to be equal to 40 divided by 4.05. That's what all of this is 4.05. Then my time estimate here, so this should be about 9.88 seconds. So if you think about that, this gun fires. Now, first of all, it fires, and these shells are going much faster than the speed of sound. But if you think of just how long they are in the air for, just think of how long 10 seconds is before you get some feedback as a gunner. 10 seconds is a long time to have your shell in the air. And how far does it go during that time? Distance horizontal is equal to your horizontal velocity times time. If that's the case, your horizontal velocity is very fast. And it's in the air for a very long time. But I got about 8.4 kilometers. 8.4 kilometers. Think of how far that is. If you are a TDCH student and know where the Woodbridge Memorial is, that's right close to the school, it's within about 150 meters of us. That means that we can fire 8.4 kilometers. That's firing into Brampton. That's firing into Maple. Like this can fire into well past Steeles into Toronto. This is a huge firing range. So the capture of these guns was really, really important. Okay. So if this is the case, if this is what we managed to get to, we're just going to put this number in our heads and say, well, what would happen if we just did this 1 degree different? So you're not responsible for doing the whole problem again 1 degree different. So 8388 is our first number to remember. And now, what happens if we change it by a degree? Not a big deal, right? Can't be that big a deal. Well, remember that my clinometer, my piece of technology that allowed me to measure very, very accurate angles. Well, what happens if that was just 1 degree out instead of 0.001? Okay, well, these aren't going to change too much. Surely 1 degree can't make that big a difference. Let's go take a look. So we look at 4 degrees instead. So this will still be up, but we need 4 degrees in here now. 1 little degree. How big of a difference can it make? Well, if we did this at 4 degrees, you should find that our opposite here is now about 59.3 meters per second upwards. And horizontally, that didn't change much, 848 instead of 849. But our upwards velocity certainly changed a bunch. And so that's up. So this is now going to be 59.3. Our velocity is still unknown right before it touches the ground. Our horizontal velocity is 848, and our time is unknown. To avoid the quadratic, we're going to use this technique again. V1, negative 59.3. Don't forget to keep that in the bracket. When you square it, plus 2 times 9.8 times our vertical drop of 40. So this time when we crunch our V2 through, it's going to be faster than last time. So we get the square root of approximately 4,300, which is equal to about 65.6 meters per second, plus or minus, and we still take the plus. So this is going to come down faster. Well, how much more time does that give us in the air? Well, if our displacement is still 40 meters, and V1 is now negative 59.3, and V2 is now 65.6, all divided by 2. Okay, and so our time in this case is going to be equal to 40, and instead of 4 meters per second, this is going to be divided by, let's see, works out to about 3.15. Does that make a big difference? Well, instead of it being the number of seconds we had before, now it's up to 12.7 seconds in the air. Our horizontal velocity is very fast. The time is longer. And so if we find this one, suddenly instead of it being 8,000 meters, we're now at 10,769. And for those that care about significant figures, I'm not allowed to claim this many numbers, but this is just proof in principle. So, plus 1 degree, what difference does it make? Well, last time I checked on subtraction, this makes a big deal. And if you're an infantry person, if you're a soldier walking towards and your artillery is plus or minus somewhere in the ballpark of 2.3 kilometers, that's a big deal. So it's really, really important that we are close. So back to our soldier, Lewis King. He was there on the very opening day of the battle. Canadians rushed up the hill and they captured it, taking very heavy losses. They learned how to fire barrels of burning oil that would create smoke screens. And they piled as many soldiers onto the hill as they could with machine guns, kept the artillery set and firing, knowing that the Germans would have to counterattack. And they did. The losses to the Canadians were immense, but the losses to the Germans were even greater. Canada once again showed that they were good tacticians, good fighters, and made a huge difference, a tactical breakthrough on the line when the British and French needed relief desperately further to the north. So there's a little bit of history. I want to share just a couple of final things with you about our soldier. They were called high energy or high explosive shells, and they were basically just a steel shell completely filled with TNT or the similar types of explosives that, like picric acid, they had at the time. Lewis King was struck by a fragment of high explosive shell in the lower third of his thigh, practically severing the same. Amputation was performed the same day, and a re-amputation through the middle third 2 weeks later. The wound was rewrapped and cleaned and healed quickly. That's a good thing. And so this is a pretty heavy thing. He was sufficiently brave to be there. The artillery were a target from the other artillery. They learned to shoot at each other. And in this particular case, our soldier lost a leg. Within a year, he was home, but his life was changed forever. We don't see shells like this as much like we used to. I am very, very thankful that I've never had to go to war. But what you see as gray in here was the explosive. The detonator would be ignited on contact. That's what you see over on the left-hand side here. And today, if you go to Lens and you go to Hill 70, you can see a monument that volunteers, not the Canadian government, donors and volunteers work together to make to honor this incredible moment in Canadian military history. So be careful, plus or minus a degree. Know your history, know your physics.